Okay, so now that we know what the quasi-static process is, we can introduce the isothermal processes and isotherms. So an isothermal process is just a process, quasi-static process in which each isothermal, let me just write it down, in which each of the intermediate equilibrium states has the same temperature, okay? And when we say a process goes along an isotherm, we say that in the VP representation, a certain process contains all intermediate equilibrium states characterized by the same equilibrium temperature, okay? So importantly, in our way of defining things, isothermal implies quasi-static, okay? So it's necessary that the process is quasi-static for it to be isothermal. So then we can talk, and this curve is an isotherm. Okay, so that's what we are going to call isotherm. So a related topic here is a heat source. So what the heat source is just a system that can exchange heat with other systems without changing its temperature. Okay, so let's see how this is possible. So we remember that when we were talking about thermal contact and the well, this is not looking very good. Thermal contact and the zeroth law of thermodynamics, we say that when we have two systems and we put them in thermal contact with each other, they will attain a joint state of equilibrium. So if the equilibria in the two states are compatible, according to our definition of temperature, it means that their temperature must be the same. And if, imagine A was way hotter than B initially, what we expect is that the common temperature that the two systems build up in the end is neither TA or TB, it's somewhere in between, meaning that the two systems are going to change the temperature and they exchange heat in that sense. So some heat is released from, say, A to B, and the temperature of A is reduced as a result, and the temperature of B is increased as a result. Okay, but imagine that system B here is just absolutely huge, okay, compared with system A. Then it is possible that the change in the temperature of one of the two subsystems, the large one, is going to be, yes, it's going to be something, but it's going to be not detectable. For all practical purposes, the large system, because it's so large, is not perturbed by the little amount of heat that it has absorbed or released into the smallest system. So it's like the cup of coffee and the air of this room. Okay, so while the coffee is cooling down, I don't expect to notice that the air has raised the temperature, although that may be true. So in the limit, okay, we say that the heat source is simply a system that can exchange heat without changing the temperature. So let me just write that down. Heat exchanged without temperature change. Okay, so then we can redefine what an isothermal process is by saying that if you have a system with diathermal walls, okay, which is in contact with a heat source or heat bath at some temperature T, and then you run some thermodynamic process in this system, some quasi-static process in this system. If the walls of this system are diathermal, then at every single intermediate point of our quasi-static process, this system needs to be in equilibrium with the environment, and the environment has a well-defined non-changing temperature, so the temperature of the system is constant throughout. Okay, so that's what the way to realize an isothermal process, to have a heat bath in contact with your system. Now, in the literature, if you go and see some many books actually, they will tell you that an isothermal process is just any process that occurs when the system is in thermal contact with a heat source. Yeah, but even if this process is non-quasi-static, so its system is out of equilibrium and the temperature is not well defined in the middle. So, okay, this is just a matter of terminology. Don't be confused by that. In this course, we're always going to be talking about isothermal process only when the process is quasi-static. Otherwise, it's just a non-equilibrium process at or in presence of a heat source. We don't give it a special name to this. So it's definitely, for us, when the process is not quasi-static, is not isothermal, okay? So then, well, it's worth mentioning what are the isotherms of the ideal gas, although we already saw this when we studied the Boyle-Mariotte, specifically Mariotte's observation on the relationship between pressure and volume at constant temperature. So remember, this is just equilateral hyperbola, right? So if I write P as a function of B, it's N, R, and then whatever fixed temperature you have divided by B. And graphically, remember, this is this hyperbole. So V and P, and you have the hyperbola here. If you have a larger temperature, well, the hyperbola is going to be higher like this, but this is not a hyperbola, but okay, you see what I mean, right? So the higher the temperature, the higher you go in the steepness of this curve. So okay, fine. So this actually, if you take any real gas which is not in this limit of being very rarefied, and you look at what the isotherm is doing in the VP representation, you rarely will see something like that, and you just need equation of state for real gases, a more realistic approximation of the behavior of real gases, which is not anymore going to be universal and depend on one single universal constant, but well, there's many equations of state for real gases. Some work better than others in some special regimes, and perhaps the simplest extension of the ideal gas equation, which I'm going to rewrite again, so it's just worth writing it down, and I'm going to take this n and divide V by n. So I'm going to define lowercase b, which is molar volume, as the total volume divided by the number of moles, and I get rid of this n that I don't want to be carrying around. So let's just write it like this. So the van der Waals equation of state would be simplest generalization, and like I said in the beginning, we are going to come back to the van der Waals equation of state later, simply because it's simple to work with, not because it's particularly accurate anyway, but it's more accurate than the ideal gas for sure. So there is a correction term in the pressure, which is like this, and then there is also a correction term in the volume. But otherwise it looks a lot like the ideal gas equation of state. Now the kind of justification for this two parameters, or these two corrective terms that have been introduced, is the following. So first, the van der Waals model considers the particles of gas to be like rigid spheres that have some tiny but finite volume. So for any one of these molecules, the available volume, if they are enclosed in a container V, is actually not V, but V minus a tiny amount. And this tiny amount is like the volume occupied by each one of the other n minus 1 particles. Okay, so it's a volumetric correction because of the actually finite size of these molecules of gas. And then the other term is correction on the pressure that comes from the interactions between the particles. So these particles, when they are very rarefied, actually they very rarely will meet or collide with each other because the density is very low, and these kinds of instances are relatively rare. But whenever you have not so rarefied gas, larger density, well, you may encounter situations in which two particles are going to interact, and these interactions are going to have an effect on the pressure. In this case, it's going to raise the pressure effectively, and phenomenologically it has been seen that this correction term, it kind of goes like 1 over the molar volume squared. Now, for every single gas, you have to find the constant A and the constant B, which works better. So the van der Waals equation of state is not universal, unlike the ideal gas equation of state, which is the nicest feature that it has. Okay, so now let's introduce finally reversible work. Okay, and for this, let's, as usual, think of our, oh, this is very bent. Okay, so like this, we think of our expansive system with a piston here and something like that. So okay, let's do like this. So I want to now, so imagine the pressure is P inside, volume at this stage is V, and imagine I let, so the gas pushes the piston a little bit out by an amount, infinitesimal amount differential of Z. Okay, so if this happens, then what is the, so what is the force that the gas is exerting on the piston? Well, it's just the area of the piston, which I don't know, times the pressure. So that is the force that is being exerted on the piston, right? And when the piston is pushed infinitesimally outside, well, the amount of work, yes, that has been done on the system is A, well, let's say by the system, is A times P, which is the force differential of Z, and A times differential of Z is differential of volume. Yes, so it's pressure differential of volume. Okay, so this is the force that the gas is doing by pushing the piston outwards. And if I ask now what is the work that the environment is making on the piston, well, it's minus that, okay? And whenever I'm going to be talking about work, it's always the work done on the system. So if the system is pushing the piston, it just means the work is going to be negative. Yes, if you are injecting work onto your system, it's going to be positive. And this is infinitesimal work, but if you want to calculate the work, you just have to write it as an integral, okay? So this minus P dV, you have to integrate it from the initial volume to the final volume. Yes, so that is the work. Now let's have a think about this work just for a moment. This expression that I wrote here includes pressure, okay? So if I want to make this integral from the initial to the final state, this pressure has to be defined, okay, throughout. And for pressure to be defined, it means that the system needs to be in equilibrium at every intermediate stage of the system. So that is to say, this formula that you have here is a formula to calculate work in a quasi-static expansive process. Okay, so it's not only for quasi-static processes. Let me just write it down. But it's actually not just quasi-static, but indeed reversible. So why is it that it's for a reversible situation? Well, because you're saying that the piston is being moved by an infinitesimal amount differential of Z, and the force done is just A times P. This is the minimum force that you would have to apply to move the piston. In general, you have to do a bit more, because there's going to be some frictional forces here that you have to counteract. So in general, you would have to push harder than that. That's the bare minimum that you would have to push with. So that's why we are implicitly assuming that this pushing process is a reversible process. Okay, so it's not just a quasi-static formula, it's actually reversible. So that's why I am going to say, whenever I write this expression, yes, minus P dV, I'm thinking about an infinitesimal reversible process. Okay, that's going to come back in the course several times, and I'm going to emphasize this whenever it comes because it's an important distinction to make. Okay, so also very important, I actually cannot highlight it enough. Please, 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 I'm going to write this with colors, okay? Work done on the system, let's write it like this, green, work done on the system. So in an expansive system, this would mean pushing the piston inside the cylinder is always positive. Yeah. And the work done by the system is always going to be negative. Yes, the work done, let's just change the color and let's just write work done by the system is negative. So I have this I'm emphasizing because you know, in exercises and also in problems of exams, you find that there's many silly mistakes with the sign convention. Again, if you look at the literature, several books have different conventions for work. For instance, one absolutely excellent book on thermodynamics, which is the book by Enrico Fermi, Thermodynamics, uses the opposite convention. So for Fermi, the work done by the system is positive, and the work done on the system is negative. I would strongly recommend you to follow our convention all the time. That way you will never be confused. But if for some reason you choose to use a different convention, at least be consistent, because it's very easy to make mistakes with signs in thermodynamics. Okay.